We should be familiar with what a carbonyl group is. So if not, go back and check up on that one. But we've got a carbon with a double bond to an oxygen. So this is our basic carbonyl group. And when we looked at aldehydes and ketones, we might find other things attached to this depending on what it is. So if it was an aldehyde, we would have an H and then one other group attached to it. Or if it's a ketone, what we're going to have are two carbon groups attached to it. Okay, anyway, so what have we got today? So today we're going to be looking at carboxylic acids. So carboxylic acid is very similar to maybe like a ketone or an aldehyde, but instead of it joining on to another carbon or a hydrogen, what we have is an OH. And this is what a carboxylic acid group is. And now what's attached to this end, so it could be anything. So I'm just putting R there to represent something else. We sometimes will write this as RCOOH, or even just RCOOH, like that. So fairly straightforward in terms of their structure. You just need to remember and be able to identify a carboxylic acid from all the other carbonyl functionalities that we're going to be looking at over the course of the A level. So that's that. So moving on to an ester. So what's an ester? Well, they're derived from carboxylic acids. So I'm going to start with my R group again. This is joined onto our carbonyl carbon. And a bit like a carboxylic acid, we've got another oxygen here. But this time, instead of it being a hydrogen, what we're going to have is another R group. So methyl, ethyl, something like that. So a carbon chain, or even just one carbon. So that's an ester. So to shorthand this, we would say RCOO, R prime. Okay, or as before, so RCOO, R prime, like that. So just get used to the structural formulas for these ones. Yeah, so that's it. So now we're going to look at how they are named. So carboxylic acids have a specific suffix to identify them. So the suffix used is oic acid. So in order to identify it, what we do is we look at the longest carbon chain. So over here we've got 1, 2 carbons, and it's the longest carbon chain containing the carboxylic acid group. And this has got 2 carbons in it, so this would be ethanoic acid. Okay, so it just runs together. So this is one word, so ethanoic acid. And obviously the most simplest acid. So here I have my carboxylic acid group, like that. So if I didn't have a carbon on there and I have a hydrogen, it would have 1 carbon in it. So in this case it would be methanoic acid. Okay, nice and straightforward there. So here I've got a skeletal formula of a carboxylic acid. And we can see we've got some branching going on here, so we're going to have to name this. So I'm going to look for the longest carbon chain that includes the carbonyl group. So that is 1, 2, 3, 4, and that is a 2 there. Okay, so this is 4 carbons long, so this will be butanoic acid. But I need to think about what this is here. Okay, so here I've got a methyl group attached to it, and it is on the number 2 carbon. Okay, so this would be 2 methyl butanoic acid. Okay, so just remember the carboxylic acid group will take the number 1 carbon, and we're going to number any substituent groups on that in order to give the lowest number we can, but the carboxylic acid group is the number 1 carbon, so that will dictate the numbers of the other groups. So here I've got a benzene ring, and if we attach a carboxylic acid group onto this, so I'll just stick one up here. So this would be called benzene carboxylic acid. It used to be called benzoic acid, so you might see that around the place, but we should call these benzene carboxylic acid. And if we draw the structural formula down here, C6H5COOH. So if you're not very familiar with benzene yet, don't worry, you may not have just covered it yet. It is a separate topic on its own, so we'll go into more deep depth of that in a future video. Okay, let's have a go at let's have a go at drawing one. Okay, so here I've got 3-chlorobutanoic acid. So what am I going to do? I'm going to do it skeletal because I find it much easier. Okay, so we've got butanoic acid. So the but bit tells me there is going to be 4 carbons. 1, 2, 3, 4. There we go. And we're going to have a carboxylic acid group. So for it to have a carboxylic acid group, we've got a carbonyl-carbon like that. And we're going to have an OH like that. So that's the butanoic acid bit done. So 3-chloro. So remember, the first carbon is, or the number 1 carbon is the one with the carboxylic acid group on it. So moving along the chain, that would be 1, 2, 3. So the chloro is going to go on here, and we will just write it like that. So 3-chlorobutanoic acid. Another go now. So 3-methyl pentanoic acid. So this is going to have 5 carbons in, because the pent bit there tells me there's 5 carbons. And let's start here. So I've got there's my carboxylic acid. So 1, 2, 3, 4, 5. 3-methyl. So this is the number 1 carbon, remember, at this end. So this would be the 3, and we're going to have a methyl group on there. So now we've got to festoon the rest of this with appropriate numbers of hydrogen. So that's going to be CH2, that's going to be a CH2, and this terminal one over here is a CH3. So 1, 2, 3. This is the methyl, 3-methyl pentanoic acid. So esters are a little tricky to name because they've got 2 parts to the name, and you've got to make sure that you get them the right way around. Now the main part comes from the parent acid. So here they've got the parent acid in kind of yellow. Okay, we would also include the oxygen as well, but I'm keeping this separate as hopefully things will come clear in a minute. So this part of the acid, so I've got my carbonyl-carbon attached to an oxygen, and then we've got a CH3 just stuck on the end of there. So this would have 2 carbons in it, so this would be, if it was an acid, it would be ethanoic acid. But what we do when we do in esters, so what we do is we change the ending of this bit, so we take off ethanoic acid and we're going to add on O8. So in this case it would be ethanoate. And that's okay, fine, happy days. But now we've got to allow for this bit over here. So this bit comes from an alcohol, and it just takes the name of the alkyl chain that's attached to it. So in this case it's just got 1 CH3, so this will be methyl ethanoate. My handwriting is terrible at the minute, this graphics tablet. Methyl ethanoate, that's our name for this one. Okay, so let's go the other way with this one. So I've got a name, ethyl propanoate, so let's try and draw the structure for this. So remember, this O8 bit tells me what the precursor acid was, so propanoate will come from propanoic acid, so that has 3 carbons in it. 2, 3, like this. And it would have had a carbonyl on it. And that's joined onto oxygen. Now, the H from the acid has been replaced by the ethyl group that I've got in the name up there. So, I shouldn't do it like this, I should do it as skeletal. So that would be 1 carbon, 2 carbons. Okay, so rewriting this out, CH3, CH2, CO, O, so this one's the carbonyl carbon, this is the ester carbon, and then what we've got on the end, CH2, CH3. Okay, so that's naming esters. Short chain esters, they're pretty volatile, so that means that they evaporate easily, and quite often they've got quite distinctive smells, often fruity. So because of this, they're often used in things like flavourings for foods and drinks, but also perfumes. They're also used for solvents. Okay, they're very good at dissolving a wide range of organic compounds. So you'll find them used in printing inks, in nail varnish, for example. So in there, it's very good for dissolving the nitrocellulose polymer in there. Also, they're used as plasticizers. So in polymers, so plastics like PVC. PVC is actually quite a hard plastic. It's used for making window frames. But by adding plasticizers such as esters, small esters, it makes them more flexible. So it makes them to be able to be bent to the point where you can get PVC like cling film. So it's very, very bendy, very, very stretchy. And this is because the small molecules of the plasticizer kind of get in between the molecules, the long chains of the polymers, so they can sort of slide across each other a little better. So, reactions of carboxylic acids. So, thinking back to structure and bonding, we should be familiar with these kind of delta positive, delta negative charges that we can apply these partial charges on them. So, oxygen's a very electronegative atom. So, this tends to draw the electrons towards it from the covalent bond. So, it becomes slightly more negative. And because the electrons have been distributed away from the carbon becomes delta positive. So this has an influence of some of the reactions. So we could have, for example, a nucleophile. Okay, so a nucleophile could be attracted to the delta positive of the carbonyl carbon. Or we could have, let's say, okay, so then we could have an electrophile which would be attracted by the pair on the oxygen. How should it be? Okay, so this is the potentials. Okay, we won't necessarily study all these. So attacked by a nucleophile, attacked by an electrophile, and the other thing that happens is this acidic hydrogen here. So these are weak acids, so they're not fully ionized. But this hydrogen ion could dissociate, or the hydrogen could dissociate from the oxygen to form a hydrogen ion, an H+. So I'll show it as an equilibrium here. So I would have my carbonyl thus, and H+. Okay, so this is a hydrogen ion, and this would be, call it a carboxylate. So this hydrogen ion, okay, I sometimes will call these just protons. So these are what makes acids acids. So this is a weak acid, so partially dissociates, hence why I've got equilibrium here, and into hydrogen ions and a carboxylate ion. Alright, so just a quick think about what a carboxylate ion is. So when we form these, so let's pretend it's O- here, and I'll show my lone pair here. Okay, so this is our ion. Now these are quite stable because we get some, we call it resonance stabilization. We'll learn a little bit about these in when we do benzene and aromatics. So this lone pair could go and form a double bond here, and that would mean the carbon would have too many bonds, so the electrons from that double bond would go up there. So say after this has moved, it's transitioned into this other one, I now have a, oops, no, I don't have that. I have an O minus here, and the lone pair sitting up with that one, and this time I have a double bond down here, and this helps stabilize the ion. So we sometimes will draw this as COO, and the negative charge is delocalized around the carbonyl group like that. Okay, so this really terrible drawing here is a negative charge. So this is stabilized. So these do like hang around a little bit. So because carboxylic acids are acids, they behave like acids. Okay, they might not be as strong as sulfuric acid, nitric acid or whatever. They're a weak acid, but they will still react with the same things. So it will react with things like bases. So up here I've got sodium hydrogen carbonate. I'm showing this reacting with ethanoic acid. It's got 2 carbons in it. And this would produce a salt, water and carbon dioxide, just like a reaction with a hydrogen carbonate would with hydrochloric acid, for example. So what am I going to make? Well, I'm going to make a salt. So CH3COO, and this time I'm making a sodium salt. Okay, so this we would call sodium ethanoate. So you might notice that the ending of this is the same as we would give to an ester. Okay, so this is the carboxylate form of it. Okay, so we've got COO in there. Now it's very important when you draw these, this is an ionic bond between the oxygen and the sodium. So don't be tempted to draw any kind of bonds in this one. Okay, so this would suggest it would be a covalent bond. That is right out. You would lose the mark on that one. Okay, and what else would we make with this? Well, we just balance it off and just remember these sort of general things you'll have been doing since GCSE days. What will I've made? I made CO2 and I would have made some water. Okay, hopefully this will all balance. I've got 3 oxygens there, 3 oxygens from that side there. All that chunk there was the same as there, so I've just swapped out a hydrogen, and yeah, that's balanced. So this is a useful test, so we could use this to distinguish carboxylic acid from an alcohol. Okay, so the exams often like to ask you how could you distinguish between A and B. Okay, and this is one of the ways that you could distinguish a carboxylic acid from some other organic molecules. Okay, so that's one thing just to bear in mind. Carboxylic acids will also react with metals because they can behave like a base. So here I've got ethanoic acid again. So I'll just label this ethanoic acid, and I'm going to react it with magnesium. So I'm going to make a salt, and the salt that I'm going to make it's going to be magnesium ethanoate. So it's the carboxylate salt, so methyl ethanoate. And what else do you produce when you react metals with acids? Well, hopefully you can remember this because you've been doing it since, I don't know, year 8 or something. I'm going to make hydrogen. I'll just fit on the screen. Okay, hopefully that didn't crop off. Okay, so we're going to have to balance this equation. So I'm going to make a CH3COO. Now, hopefully you can remember what the charge is on magnesium when it forms a compound. Okay, so magnesium is in group 2. You could say it's got 2 electrons in the outer shell, which it would lose. So it would be oxidized to the 2+ ion. But the carboxylate only has 1 acidic hydrogen. So it's only got a 1- charge. So what we're going to need for this is we're going to need 2 lots of these for every 1 magnesium. So just like you would do if it was like a nitrate or something like that, you would show the anion in brackets and say the number of them that you'd have next to it. And then we've just got the magnesium there. You could write MgCH3COO2 like that. So as long as you've got it protecting those brackets, happy days. And we're going to make some hydrogen. So because we've got 2 of these groups over here on the right hand side, we're going to need 2 of those there. Okay, and that should be balanced. So we've got 2 hydrogens now, 2 acidic hydrogens there, which could be reduced to form our hydrogen gas. So we could always have some state symbols on here if we like. It's always good to get some state symbols. What am I adding? I'm going to add it as a aqueous solution, let's say. I'm adding that as an aqueous solution. My product would be an aqueous solution as well. Okay, so just watch out for the stoichiometry, the balancing of these equations if you need to do them. So now we're going to have a quick look at making and breaking esters. Okay, so starting with making. So where do we get an ester from? Well, we get them, and you might have alluded to this in the past, or I might have alluded and you might have picked it up. We get it from an carboxylic acid and an alcohol. And these will react together, and we would usually do it in the presence of a catalyst such as H2SO4. So just a couple of drops of concentrated sulfuric acid into our mixture of carboxylic acid and alcohol, and we would then make our ester, R prime. And what we will release as well as this, that's supposed to be prime, not a plus, there we go, that's better, is water, H2O. When we release a small molecule like this, we call this a condensation reaction. So here I've got yellow, I've got my ethanoic acid, and I've got some methanol shown over here. So what we can look at is how these sort of combine together. So we can see that we've got an H from there and we've got an OH here, and these things can combine to form our water. So they'll combine in the way shown here, so we make our ester. So this time we've got this, so we will have methyl ethanoate, just as a practice for naming these. So 2 carbons in our acid end, so ethanoate, and 1 methyl group in from our alcohol, and then we form our water as well over here. So going back to the equation that I had up here, we can see that I showed it. Oh, I've not got my pen selected. I've shown it as a reversible reaction, which I mentioned. So if it's a reversible reaction, it can be reversed. So I can react my ester. So let's go back to what we had before, CH3COO-CH3. So my methyl ethanoate. I can react this with water to turn it back into our constituent acid, ethanoic acid, and the alcohol, methanol. Okay, so this is hydrolysis. So hydrolysis, so hydro comes from water, and isis kind of means break apart. I'm not writing apart. Okay, so this is hydrolysis reaction, and these are quite useful, and we will look at some examples of what we can do with it. So we could take our hydrolysis reaction and we could catalyse it with a strong acid, a bit like we did the forward reaction or the backward reaction, whichever way you think about it, the esterification reaction, let's say. So I could catalyse it with sulfuric acid and get an equilibrium mixture. Okay, so always expect some equilibrium calculations to fall out of stuff like this. Now, the other thing that we could do is we could base catalyze this reaction. Okay, so instead of H2SO4, we could use sodium hydroxide. Now, the thing with sodium hydroxide, if we use this one, what that's going to do, excuse me, is we're going to react and form the sodium carboxylate salt of this stuff, like that, and then we can tag on our methanol that we would have produced as well. So this time, you see I've not drawn an equilibrium arrow here, I've drawn a forward reaction, because we can consider this almost being like a neutralization, which pretty much goes all the way. So this forms the carboxylate salt of the base. So if it was sodium, it would be a sodium ethanoate, as in this case, or a sodium carboxylate salt, or if it's potassium hydroxide, it would be potassium carboxylate salt. So if we use sodium hydroxide in here, what we're going to do is we're going to create quite a lot of... So using sodium hydroxide, we're going to create a lot of carboxylate ions. So referring back to the equilibrium that we have up at the top up here, if we're producing lots of carboxylate ions, we're not going to have a lot of carboxylic acid. So if my concentration of this decreases, what's the effect on the equilibrium? Which way will the equilibrium shift? Well, if I'm decreasing the concentration of this on the right hand side, equilibrium will shift according to Le Chatelier's principle to compensate for that change. So it's going to move the equilibrium even further in this direction. So my concentration of my ester is going to decrease. If we're doing an aqueous solution, then water will already be very high anyway. But so it's going to promote this forward reaction in this case, okay, the hydrolysis reaction. So that's why we kind of consider these as being to completion. So this molecule here is 1,2,3-propane trial, and this is quite an important molecule because esters of this stuff are what make up oils and fats. So let's go back here. So oils and fats, we sometimes call these triglycerides, and they'll be esters of these. So joined onto here, I would have for each oxygen on the alcohol, the propane trial, I would have a ester group. Okay, so there's my carbon, oxygen, carbon with a carbonyl. Just zip those out. And attached to all these things, there may be a long carbon chain of something or other. Okay, I'm just going to say I've got a whole pile of CH2s. Let's say, I don't know, 16 CH3. And they may be the same. Like that. Or you do have to kind of keep your eyes peeled sometimes, and they may sneak different numbers of them. So keep your eyes peeled for that one. So for example, here I've got a 19 carbon chain attached to the carbonyl carbon here. Okay, and we call these triglycerides. So there's an ES on the end there. So yeah, like I said, these make up oils and fats, and they're really quite useful, and we can use these for other things. We can hydrolyze these in the same way as we just seen with other esters. Okay, so hydrolyzing these to produce different substances, so different acids in particular is the thing that we're going to be looking at. So if we do this hydrolysis in the presence of a base, we're going to make a sodium carboxylate of the fatty acids. So in case we've not mentioned, the fatty acid is like the green bit at this end, okay, with a carboxylic acid group at the end. We would make the sodium salt of these, which is used as soap. Okay, so it's really important process this. I'll just go into a bit of depth on that next. So here we are back with that same triglyceride that we looked at before, remembering that I had two different legs on it, if you like. Okay, so I've got a 16 CH2s, 16 CH2s, 18 CH2s here. Now, we're going to do a hydrolysis, so we're going to be breaking it apart across here. Okay, so we're going to leave behind our glycerol, our 1,2,3 propane triol, and we're going to be getting our salt of the carboxylic acid that's formed on the other end. Because there are three legs on this, I'm going to need 3 lots of sodium hydroxide. So that's important to remember on this one. So I'm going to have my reaction arrow there like that. So I'm going to produce a molecule of glycerol. So that has now formed the triol, the glycerol. I will also have a sodium salt of some fatty acids. So here I have O, C, O, and what did I have? I had CH2, and for this one I had 16 of these. The CH3 bobbed on the end there, and the other one I had 18 of these with the CH3 on the end, and oops, no, wrong one, I want this, a blue pen, and I've got the sodium salt of that. Now, just to make sure that we've got it right, we've got to make sure we've got the right numbers of things, and I'm going to have 2 of those with 16 and 1 of those with 18. So here I've now broken apart my triglyceride. So this was my triglyceride. This will have come from an oil, so palm oil, quite often, environmentally unfriendly as it is. Reacted it with my sodium hydroxide. I've made my glycerol, my 1,2,3 propane triol, and I've made my sodium carboxylate salt. So these things here are what make soaps. Okay, so now I'll just talk a little bit about what soaps do. So soaps are a type of surfactant. So you don't need to really know this is a key word, but where it comes from is they are surface active agents. So they are things that work on surfaces. And the kind of principle of these is related to the structure of the molecules there. So I'm going to imagine I've got a big long wibbly wobbly carbon chain, and at the end of this carbon chain, I'll just change the colour, go for blue, I have my carboxylate salt here. So this is my sodium salt. So this is my soap. So in this case it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, say 12 carbons long. So what we do is we look at this end here, and because this has got lots of electronegative oxygens here, we've got an ionic group here with this O minus Na. So this is very, very polar. Okay? It's got charges in there. So this would like water. So this is hydrophilic. It loves water. This is hydrophilic. Now this other end, this the yellow wibbly wobbly carbon chain. This, however, doesn't have any polar bits in it. This really, really, really doesn't like water. Okay, there's no interactions. There's no benefit for this breaking up the hydrogen bonding that's present in water. It's really, really insoluble. So this hates water. So this is hydrophobic. Water hating. Got a dot up here, and there we go. So this is hydrophobic. So what could we say? Well, we have a hydrophobic tail, and then we have a hydrophilic head end here. Okay, so this is how we could sort of perceive our surfactants to be. I tend to normally draw them as a bit more of a wibbly wobbly thing. So how do these work? Well, what we're going to do is we're going to imagine we've got a stain. So I went for my lunch and had a kebab, and I dropped a big blob of oozing kebab juice onto my best suit. So here I've got my yellow orangey blob of grease, and the light blue just represents the fibres. So adding water won't do anything because it just won't attack the grease. Okay, it's very, very oily, it's hydrophobic, it won't like water, it hates it. So what I'm going to do is I'm going to add in my surfactants. Now my surfactants, I'm going to show them one colour because otherwise it'll take me a billion hours. I have the hydrophilic head end, which I'll show as a blob, and then I've got my hydrophobic tail. So the hydrophobic tails, because they don't like water either, they are going to sit into the greasy, oily stain from my kebab juice. And sticking on the outside will be the hydrophilic heads. I'll make them a little bit bigger there. So with a little bit of mechanical action, a bit of rubbing and a bit of scrubbing, what happens is we get our blob of grease, into which we have our hydrophobic tails from all our surfactants. I'm now regretting using green. So they'll all stick on the inside. And on the outside we've got our hydrophilic head bits. So they're the charge groups, they're the carboxylate, I beg your pardon, groups from each of the fatty acid chains. So because these are negatively charged, now this droplet that we've formed here can now interact with water. Okay, this would be like a stabilized drop of oil in water. Okay, so when we get stabilized droplets of oil, so these are suspended, they're not coming together, these negative charges around the outside stop them clumping together. We call these emulsions. Okay, so emulsions are stabilized droplets of one liquid in another. Okay, so the things that don't dissolve, so they're immiscible, and they form these emulsions. Okay, you might be familiar with emulsion paint that you use for decorating paint on walls or whatever. It's a similar process there. Okay, a similar principle at least. So going back to the other product of our making soap reaction, okay, so we made our glycerol. So the 1,2,3 propane triol. Now this stuff also has uses. This is in the industry we call it a humectant. Not a key word you need to know, but I always like shoving this stuff in. So it keeps things moist. Okay, so what this is very good at, it's often used in cosmetics. So if, like me, you find that your makeup dries out a bit too quickly and cracks, adding glycerol in there will stop it drying out so fast. It's used in all kinds of other stuff, so pretty much all shower gels and all that kind of junk, you'll find this stuff in to some extent, often labelled as glycerin actually. Even less of a useful name. Okay, so it could be labelled as glycerin, so it's used to stop things drying out. It's sometimes used as a solvent, so it will dissolve things. It's very hydrophilic itself. It's kind of infinitely soluble in water. So it's sometimes used in inks. Sometimes used as a food additive. I've heard of it being used in bread to stop bread going stale so quickly because it keeps it moist. So yeah, it does have quite a lot of uses on its own. Now, the last thing I want to talk about on these is what happens if we react this with methanol. Okay, so I'm going to react 3 methanols with this, and we will react this in a kind of with a catalytic amount of sort of like potassium hydroxide. So we take the potassium hydroxide in a small amount because it's just to sort of catalyze the reaction. And what we're going to be doing is we're going to be doing hydrolysis again, so breaking these apart, but we're also going to be esterifying it. So we're going to be making our So we'll be making our glycerol as before, but we'll also be making a ester. Okay, so attached onto here, so this is our from our fatty acid, we're going to be getting ester group, and it will be a methyl ester of it. And because we had 3 of them, we've got 3 legs, and this time I have made them all the same. We would make 3 molecules of this stuff. Okay, so this methyl ester. So the use of these is for biodiesel. Okay, so industrially it's getting more and more important because we can get oils that are derived from plants, and then we can turn them into fuel that we can put in trucks to drive more junk around from Amazon. So this is an important product, and you just got to watch out. So this is in the presence of methanol, you're going to be talking about biodiesel. Okay, so that's what you're going to be the question's going to be about. If you're just talking about sodium hydroxide, then that's the other case, and that's when we'll be making soaps. So just be on the lookout and make sure that you can spot these. So to summarise, what we've looked at today is we've looked at how carboxylic acids and esters can be named. We've looked at how we can react carboxylic acids, so what the nature of the carbonyl group means to the reactivity of carboxylic acids, how they can behave as acids, how they are weak acids but still undergo similar kind of reactions as mineral acid type things, particularly with sodium hydrogen carbonate, and how we can use that as a test for a carboxylic acid compared to, say, an alcohol group. How we can name the salts formed from these, so how we make our magnesium carboxylate and so on. We've looked at how we can make esters by reacting an alcohol and carboxylic acid in the presence of a strong acid catalyst, and how we can then break this apart again in a hydrolysis reaction, so how the ester can react with water to then form the carboxylic acid and the alcohol. We've looked at how if we used a base to catalyse the hydrolysis reaction, we're going to get a salt of the acid produced rather than the acid itself, and how we use this when hydrolysing oils and fats to produce soaps, where a triglyceride will break down into glycerol or propane 1,2,3-triol and the sodium carboxylate salt of the fatty acid. We've also looked at how we can esterify natural triglycerides to produce biodiesel by heating it in a catalytic amount of potassium hydroxide and methanol to make a methyl ester of whatever fatty acids were in the triglyceride. Okay, hope this was okay. Feel free to comment unless they're objectionable. Have a great day, and I will see you in the next video.